Hello, I'm Michelle Crummell. In this video, we're going to learn how to find the antiderivative of a function. For this first set of problems, we're going to determine which of the following functions are polynomial type functions. So we can't technically call them all polynomials because there are some limitations on how we define a polynomial function. But basically, for polynomial type function, we want a function where each term is in the form of a constant multiplied by a variable raised to some constant power. So in the first equation, 3x to the fifth satisfies that form, right? 3 is a constant multiple, and then we have x raised to a constant power of 5. The next term, the minus 6x squared, again, that term is in the form of a constant times x to a constant power. And then the last term plus 1 is also in that form. Now we don't see an x in that term, but we can think of it as x to the power 0. And so we still have that form of a constant times x raised to a constant power. So number 1 is a polynomial type function. And more than that, it is actually a polynomial function. Number 2 is a little bit different because the second term is not written in the form of a number times x raised to a power. Here we're dividing by x raised to a power, but we know we can use algebra to rewrite this as y equals negative 2x to the power 4 plus 7x to the power negative 3 minus 5. And now each term is in the form of a constant multiplied by x raised to a constant power. So this is a polynomial type function as well. However, it is not a polynomial function because polynomial functions do not contain negative exponents. Okay, so we're being a little bit loose when we say polynomial type function. And basically, we just want to know if this function is one for which we could use the power rule. That's where we're going with this. All right, number 3, y equals the square root of 2x. This is not a polynomial function, but we can rewrite this as y equals the square root of 2 times x to the power 1/2. And that is an equivalent form. And so now it's polynomial type because we have the constant multiple, root 2, and then x raised to a constant power of 1/2. It's not a polynomial function because polynomial functions have whole numbers as their exponents or 0. Number 4, y equals 2e to the x plus 1. This is not a polynomial type function because we don't have x as the base. So this is an exponential function. We have 2 is a constant multiple. E is a constant base raised to the power of x. That's not what we're looking for here. We're looking for x in the base raised to a constant power, and this is flip-flopped, right? This is a constant base raised to a variable power, x. So this one is neither a polynomial function nor a polynomial type function. But 1, 2, and 3 were all polynomial type functions. And what's nice about polynomial type functions, it's very easy to take the derivative using the power rule. And what we're going to see is that it is equally very easy to find the antiderivative by just reversing the steps of the power rule when we are working with these polynomial type functions. So let's recall how we take the derivative using the power rule. Step 1, we multiply the coefficient, if there is one, multiply the coefficient that's already there by the original exponent, and then we decrease the original exponent by 1, meaning we subtract 1 from the exponent. That's how we use the power rule to find the derivative of a term in a polynomial type function. So to find the antiderivative, we're just going to undo each of those steps in the reverse order. So to undo decreasing the exponent by 1, we are going to add 1 to the exponent. And then to undo multiplying the coefficient by the original exponent, we are going to divide by the new exponent. And we'll see how that works with an equation in just a moment. Okay, so we're undoing those steps. We're going to add 1 to the exponent, and then we are going to divide by the new exponent. So first, let's find the derivative of each one of these equations. Y equals x cubed minus 3x squared. We're going to use the power rule to find the derivative. So we can say y prime or dy dx. There's different notations for derivative. Y prime equals 3x squared minus 6x. There's our derivative. Now let's take the derivative of the next equation. We get y prime equals 3x squared minus 6x plus 0, and I'm not going to write the plus 0. It's not necessary. Okay, the derivative of the next equation, y prime equals 3x squared minus 6x, and then minus 0. So even though all three of these equations are different, they all have the same derivative, which is fine, except that if I tell you what the derivative is and I don't show you the original equation, I just say, here's the derivative. You tell me what the original equation was before we took the derivative. We can see that there's a problem there because we don't know if there's supposed to be a plus 0 at the end, the constant term, or a plus 4, or a minus 12, or a plus 6.38. There are actually infinitely many equations that all have this same derivative because we could use a different constant term at the end. The derivative of any constant is 0, and so when we're trying to undo a derivative, if the derivative is 0 and you try and undo that, we just don't know what the constant was. Okay, so hence find the antiderivative of y equals 3x squared minus 6x. Well, we know the way we got 3x squared was by taking the derivative of x cubed. So that's going to be part of our equation. And we know the way we got negative 6x, that came from taking the derivative of negative 3x squared. And now, again, we've got like a plus 0 at the end of the equation there. And what did we take the derivative of to get 0? We don't know. So what we do is we put a placeholder there. We're just going to put plus c, c for constant. The constant of integration is what that is called. The constant of integration. And we need more information in order to figure out what the value of that constant is. So in general, if we don't know what it is, we just keep plus c in our answer as a placeholder for the constant term. So let's define the antiderivative of a function. The antiderivative of a function, big F of x, is denoted as, and we're going to be using this notation, and we're not going to talk too much about the notation in this lesson, but what we will see in the next lesson is where this notation comes from and why we use it. So for now, we're just going to accept that that is the notation that we're using if we want to indicate the antiderivative of the function big F of x. We put this sort of elongated S-shaped symbol in front of it, and we're putting dx at the end of it. And so whatever comes in between those two things is the thing we are taking the antiderivative of. Okay, so the antiderivative of big F of x is denoted as. And we have a couple of different ways we can say this out loud when we're reading it. I usually just say the integral of f of x dx, but we could also say the antiderivative of f of x. F of x is the derivative of some function, and we're trying to figure out what that function was. What was the original function that produced f of x as a derivative? And so whatever you see here, whatever you see in this integral problem between this integral symbol and this dx here is a derivative. Even if it doesn't look like a derivative, right here when you just see f of x, it doesn't look like it's a derivative because we don't have the prime symbol there. But we can call our derivative function anything we like, so just think of it as a derivative. It's the derivative of something, even if it's, not showing you a notation that looks like a derivative. It's still a derivative. So whatever is in here is a derivative, and when we put that notation around it, we are asking to undo the derivative. So it just gives us, if this is f prime of x here, it's going to give us f of x, and then we're going to include plus c at the end for the constant of integration because we won't know what that is equal to. Now, eventually we'll see that we can solve for c if we have a little extra information, but in general, we'll just keep the plus c as part of our answer. Let's do a few examples. This would be a good time to pause the video and try these on your own before we go through them together. The first one, we want the antiderivative of 3x squared plus 2x and plus 3. So we'll just do them one at a time using that reverse power rule. So the way the reverse power rule works, we've got our constant multiple there, it stays the same. We are going to add 1 to our exponent. So instead of 2, I'm going to go ahead and write the plus 1 just so you have it in your notes. We're going to add 1 to the exponent, so it's going to become x cubed. And then we divide by the new exponent. 2 plus 1 is 3, so I'm going to divide by 3. And that will give me that term, that first term. Plus 2 is a constant multiple, so that remains. X, we're going to increase the exponent by 1. Now, x is the same as x to the power 1, and we're going to increase that by 1. So the new exponent is going to be a 2, and then we're going to divide by the new exponent. It's just coincidence at this point that the coefficient in the numerator and denominator match. That doesn't always happen. Plus 3. Now here, 3 is a constant, but we could think of it as a constant multiple like 3 times 1. And 1 is the same as x to the power 0. So we're going to still use our reverse power rule. We have x to the power 0. We're going to add 1 to the exponent. The new exponent is a 1, and so we're going to divide by 1, and then we will include a plus c at the end. Okay, so normally you don't have to show that much work, but I just wanted to be clear about how we're getting our answer. So this is going to simplify to be just x cubed plus x squared plus 3x plus c. Now, a good way to check your answer whenever you're finding an antiderivative is to just take the derivative. Take the derivative of your answer and see if you get back to the equation you have inside of your integration problem. So the derivative of x cubed is 3x squared. That looks good. The derivative of x squared is 2x. That looks good. The derivative of 3x is 3. That looks good. The derivative of c is 0. So we've got it. The next example. Now, we have a quotient rule for finding derivatives. There is no quotient rule for finding antiderivatives. What we need to do here is rewrite this problem so that it is in polynomial type form. And that's why we started with that exercise at the beginning of the lesson. Can you recognize when you can get into polynomial type form and when you can't? So if possible, we want to write this in polynomial type form so we can just use the reverse power rule. So I'm going to divide each term by x. There are other ways you can do this. If you like to think of this denominator as x to the power 1, then subtract your exponents, you can do that as well. But I like to just think about it as each term in the numerator is divided by x. So x cubed divided by x is x squared. 2x divided by x is 2. And then negative 4 over x. Negative 4 over x, I want this in polynomial type form, so I'm going to move the x into the numerator using a negative exponent. So it's going to be 4x to the negative 1. So we haven't found the antiderivative yet, so it's important that you're still using proper notation here. Now we're ready, now that it's in polynomial type form, we are ready to find the antiderivative. So the antiderivative for x cubed, we're going to add 1 to the exponent, or for x squared, sorry, I'm thinking ahead. We're going to add 1 to the exponent, giving us x cubed, and then you divide by the new exponent. That's it. Here, it's x to the power 0. So you're going to add 1 to the exponent, it's going to become x to the power 1, and then you're going to divide by the new exponent, so divide by 1. But I think an even easier way to think about this is just, what would you take the derivative of to get 2 as an answer? Well, you would take the derivative of 2x. If your derivative is equal to a constant, that comes from taking the derivative of a linear term. Okay, and then the next one, minus 4 is a constant multiple. X, if we add 1 to the exponent, we're going to get 0. Negative 1 plus 1 is 0. Then we're supposed to divide by the new exponent, but that's a problem. We can't divide by 0. So that doesn't work. This is like the one exception when you cannot use the reverse power rule in polynomial type form. That's if you have x to the power -1. You can't take the derivative, or I'm sorry, you can't take the antiderivative of x to the power -1 using the reverse power rule. So we need a different method. And I think the best method is recognition, where you say to yourself, so I'm going to just come back up here, and instead of writing x to the -1, I'm just going to put it back like it was, like this. Actually, I'm going to factor out the -4 and write it like this, -4 times 1 over x. So the -4 is a constant multiple, and when you're taking a derivative, a constant multiple remains a constant multiple. So same is going to be true for the antiderivative. So the -4 is there, times, now we need the antiderivative for 1 over x. So my question for you is, what would I take the derivative of to get 1 over x? And that is one that you should have memorized. The derivative of what equals 1 over x? Well, the derivative of ln x equals 1 over x. So the antiderivative of 1 over x is ln x. Almost. Okay, I'm going to write ln x, and then we're going to talk about why that's not quite right. It is true that if you take the derivative of ln x, you get 1 over x. But we have to be careful when we're starting with 1 over x and reversing that to get the antiderivative. And the problem comes about because the domain of the function y equals 1 over x is different than the domain of the function y equals ln x. If we consider the graph of 1 over x, it has a vertical asymptote on the y-axis. And then that graph looks something like this. So the domain is all real numbers except for x equals 0. When we look at the graph of y equals ln x, that also has a vertical asymptote at x equals 0, or the y-axis, but the domain is different. The domain is all numbers greater than 0, all real numbers greater than 0. So we could run into a problem if we say the antiderivative of 1 over x is equal to ln x, because if we're starting with 1 over x, there's no reason why x couldn't equal -2, for example. That's part of the domain of that function. When x is -2, we've got a point on the curve, no problem. However, the antiderivative function doesn't exist when x equals -2 because you cannot take the log of a negative number. So we need to make sure, or we need some way to change the domain so that they match. So we're working with the same domain, and we accomplish that by taking the absolute value of x. So that if you had a problem where x was -2, then here you take the absolute value of -2, which makes it +2, and then you take the log of +2, and you're fine. Okay? So we want to, this is just going to be a memorization one. We want to remember that the antiderivative for 1 over x is the natural log of the absolute value of x. And then, of course, I need my constant plus c at the end, my constant of integration there. For the next problem, we have the product of two functions, and even though we have a product rule for finding derivatives, we do not have a product rule for finding antiderivatives. So we're going to have to multiply this out so that we get polynomial type form. So we're going to expand x plus 2 times 2x minus 3. So it'll be 2x squared minus 3x plus 4x minus 6. That is an equivalent form, and now it is polynomial type form, and it is a polynomial function. So we can take the antiderivative of each term just using that reverse power rule. 2 is the constant multiple. We're going to add 1 to the exponent, making it a 3, and then we're going to divide by the new exponent. For x, think of it as x to the power 1. We add 1 to the exponent, divide by the new exponent. Minus 6. The antiderivative of a constant term, remember, is going to be a linear term. This is just minus 6x. And then plus c, our constant of integration. And as I said earlier, if you're not sure, You can always check your answer by taking the derivative of it. Take the derivative of your answer and see if it matches that function you started with. Okay, then our last example here. The antiderivative of 2 over the square root of x. So we want to write this in polynomial type form. 2x to the power negative 1/2 dx. Now we can just use reverse power rule. So the 2 is a constant multiple. We're going to add 1 to the exponent. Negative 1/2 plus 1 is positive 1/2, and then we're going to divide by 1/2. But dividing by 1/2 is the same as multiplying by 2. So we get 4x to the 1/2, which is the same as 4 times the square root of x. And I need to add my constant of integration. So we need to carry that through. Plus c, plus c, plus c. I don't actually do this one this way, so let me show you another way. And the way I'm going to do it is just based on recognition, because I know that the derivative of the square root of x is 1 over 2 root x. And that tells me that the antiderivative of 1 over 2 root x is the square root of x plus c. So I almost have 1 over 2 root x. I'm only off by a constant multiple. And when you're off by a constant multiple, you can always adjust for that. I'm missing a constant multiple of 2 in the denominator, so I'm just going to multiply the denominator by 2. And it's very easy to balance the fraction if I just multiply the numerator by 2. And you can multiply it here in the numerator there, or you could even bring it to the outside, because constant multiples can be factored outside of the integral. That is one of our properties of integrals that we'll see in a bit. Okay, so now this 2 is a constant multiple, and I can bring that out as well. So I'm seeing this in my head as 4 times 1 over 2 root x dx. And as soon as I see that I'm taking the antiderivative of 1 over 2 root x, I know that's going to be just the square root of x. So my answer is going to be 4 times the square root of x plus c, which I find a little quicker than the way I showed you a moment ago, working with the negative exponents and dividing by the fraction. Let's look at the antiderivatives for our sine and cosine functions. We know that the derivative of sine x is cosine x, and so the antiderivative of cosine x is going to be sine x. That one's easy. Plus our constant of integration. And we know that the derivative of cosine x equals negative sine x. So the antiderivative of negative sine x is cosine x. Now the negative there is just a constant multiple of negative 1. So if I ask you what is the integral of sine x dx, the antiderivative of sine x is going to be negative cosine x. Then plus c for our constant of integration. It can be easy to mix up the derivatives and antiderivatives with sine and cosine because they are very similar. What I like to do whenever I am integrating cosine x or sine x, or some constant multiple times one of those two, is to take the derivative of my answer. I do stop and take the time to do that because I will catch my mistakes if I do that. And by mistakes, it's usually just having a negative sign when you're supposed to have a positive sign, or vice versa. So I will write down what I think it is intuitively, and then just mentally I always say, okay, what's the derivative of sine, and make sure that it gives me the right answer here. What's the derivative of negative cosine? Well, I know the derivative of cosine is negative sine, so negative sine is sine. So I know that's right. A few examples here. Our constant multiples remain. So the antiderivative of 2 sine x plus cosine x, well, think about what's going to give you this as a derivative. The derivative of cosine is negative sine, so it's going to be negative 2 cosine to make sure that that answer is positive. Then the derivative of sine is cosine, so it's going to be plus sine x plus c. For x, we're going to use our reverse power rule, so it's 4x squared over 2. Or you can think, if it's easy for you, what would you take the derivative of to get 4x? And then the derivative of sine is cosine, so we don't need to change the sine, S-I-G-N, sine here, negative 3 sine x. And again, I just do a quick take the derivative of that. The derivative of sine is cosine, so I can see that that is correct. Okay, then we're going to integrate t squared dt. So that gives us t cubed over 3. We add 1 to the exponent, divide by the new exponent. That's reverse power rule. Then here, the derivative of cosine is negative sine, which is what we want. So I'm integrating cosine. I'm taking the derivative of cosine t to get negative sine t. Plus c. And then for the square root of x, now I showed you kind of a shortcut when the square root of x was in the denominator. I don't find that there's an easy way to remember this one when it's in the numerator, so I usually go ahead and just think of this as x to the power 1/2 and use the reverse power rule. So it's going to give me, I'm going to add 1, so I get x to the 3/2. Then I'm going to divide by 3/2, but dividing by 3/2 is the same as multiplying by 2/3. Plus, and then the derivative of cosine is negative sine, so I need to change the sign there. Plus c. And then just take the derivative again as a check. The derivative of negative cosine x is negative sine x, so that is correct. Okay, let's use the information that we have here to find f of x. So starting with f double prime of x equals 2, if we take the antiderivative of f double prime of x, we're going to get f prime of x plus the constant of integration. So let me write that down. If we integrate f double prime of x dx, we're going to get f prime of x, and the f prime of x is going to have a constant of integration there. So we'll have a plus c at the end. So f double prime of x equals 2 means we can integrate 2 dx, and that's going to give us f prime. So when we integrate 2 dx, we get 2x plus c, and that's equal to f prime of x. Now we know that f prime of 2 equals 5. So let's substitute 2 in for x and set that equal to 5. So f prime of 2 equals 2 times 2 plus c equals 5. 4 plus c equals 5, so c equals 1. Now we know that f prime of x equals 2x plus 1. We can replace the c value with a 1. And if we integrate f prime of x, we're going to get f of x. So the integral of f prime of x dx equals f of x plus the constant of integration. And I'm going to be careful here not to just say plus c, because I already called the first constant of integration c, and they don't necessarily have to have the same value. They could have different values. So it's like a constant 1 and a constant 2. Okay, so the integral of f prime of x dx is going to be the integral of 2x plus 1 dx, and that is going to give us f of x. And when we integrate 2x plus 1, we get x squared plus x plus c. So that's our f of x. And then we have here that f of 2 equals 10. So now if we substitute 2 in for x, 2 squared plus 2 plus c, we are going to get 10. So it's 4, 6, 6 plus c is 10, c is 4. So now we can come back to our f of x equation here, and we know that f of x equals x squared plus x plus 4. Now I said I wasn't going to call it c, and I did, so I didn't mean to do that. So we're going to go back to the original constant of integration, and I'm going to call that constant 1, so c sub 1, c sub 1. And then it's okay if I call the new one just plain c. I could call it c sub 2 if I like, but they're different, so it's okay to put a subscript on one of them, and then the other one we can just call c. So the final answer, f of x equals x squared plus x plus 4. This is a similar problem. We start with a second derivative equation. We're going to integrate the second derivative, and that is going to give us the first derivative equation plus the constant of integration. So the antiderivative for x to the negative 3/2, we can use the reverse power rule here. We're going to add 1 to the exponent. Then we're going to divide by the new exponent. Dividing by -1/2 is the same as multiplying by -2 plus c, and that's equal to f prime of x. So we know f prime of 4 equals 2, so we'll substitute 4 in for x and set the function equal to 2. 4 to the -1/2 plus c equals 2. 4 to the -1/2 is 1 over 4 to the 1/2, and 4 to the 1/2 is the square root of 4, which is 2. So this is just 1/2 times -2 plus c equals 2, and that is -1 plus c equals 2, c equals 3. So now we know that f prime of x, I'm going to write it over here, f prime of x equals, here's our f prime of x equation, I'm going to write, no, I'm not going to write it differently because we have to find the antiderivative again. So -2x to the -1/2 plus, instead of c, now I can say plus 3. That's the f prime of x equation. To get the f of x equation, we're going to find the antiderivatives of these two terms. So we're going to integrate -2x to the -1/2 plus 3 dx, and that is going to give us f of x. So we can use reverse power rule here, -2. Then we're going to add 1 to the exponent. -1/2 plus 1 is 1/2. Dividing by 1/2 is the same as multiplying by 2. Plus, reverse power rule here, we get 3x plus c equals f of x. And we know f of 0 equals 0. So if I substitute in a 0, I get 0 plus c equals 0. Therefore, c equals 0. Oh, I did that again. I called them both c. So let me go back and call this c sub 1. Okay, now here's c is 0, so that makes that pretty easy. This is our f of x function here. -4, x to the 1/2 is the same as -4 square root x plus 3x plus 0 equals f of x. In our next example, we're told an evergreen nursery sells a certain shrub after 6 years of growth and shaping. The growth rate during these 6 years is approximated by the differential equation DHDT equals 1.5t plus 5. So this is the growth rate, indicating it is a derivative, and we can see that from the notation dh over dt tells us it is a derivative. T is the time in years, h is the height in centimeters. So this derivative, DHDT, is measured in centimeters per year. Those would be the units, centimeters per year. The seedlings are 12 centimeters tall when planted at time t equals 0. So there's 12 centimeters tall, that's the height. The height is 12 when the time is 0. That means h of 0 equals 12. We're going to need to use that information for this problem. So number 1, find DHDT when t equals 3. We have the equation for DHDT. So DHDT when t equals 3, we simply substitute 3 in. 1.5 times 3 plus 5. So that's 4.5 plus 5 is 9.5. Explain what this value represents. So always good to think about units. This derivative is centimeters per year. What does this represent? So I'm going to write my sentence at the bottom. At time t equals 3 years. And we need to include that because we need to say that it is an instantaneous rate of change, not an average rate of change. You don't have to word it exactly like that. That might sound a little bit awkward if we're trying to go for nice, eloquent English. But this gets the point across that it is instantaneous. At the time, the exact time when t equals 3 years, the height of the shrub is increasing. And I know to say increasing and not decreasing because this derivative is positive. So is increasing at a rate of 9.5 centimeters per year. So a lot of parts there. We've got instantaneous, then context, it's the height of the shrub. Is it increasing or decreasing? And that's based on whether the derivative is positive or negative. We're saying that it is a rate. We're giving the quantity and then the units. So you need all of that in your explanation. For the next part, we're going to find an equation for h of t. Now, dh over dt is the same as h prime of t. So we just need to find the antiderivative of h prime of t to get h of t. So we're going to integrate 1.5t plus 5 dt. Again, we will talk more about this notation in the next lesson. But you want your variables to match. So I switched from dx to dt because my variable is a t. Okay, so this we're going to use reverse power rule. So 1.5 t squared, we bump up the exponent by 1, then divide by the new exponent, then plus 5t plus c, and that is going to give us h of t. Now, in order to solve for the value of c, we can use this information that was given here. We know h of 0 equals 12. That's going to allow us to solve for c. So I will substitute 0 in for t, and I get 0 plus c equals 12. So c equals 12. In this problem, c equals 12. So now I can replace this c value with a 12. Let me move up here and write the equation. H of t equals, so 1.5 is the same as 3 over 2. 3 over 2 divided by 2 is 3 over 4. Squared plus 5t plus 12. And now the question that we're trying to answer, determine how tall the shrubs are. So find h when they are sold. Well, they're sold, we're assuming, after 6 years. Oh yeah, it says they sell the shrub after 6 years. So we want to find h of 6. Okay, so it's 3/4 of 6 squared is 36 plus 5 times 6 plus 12. So that's 27 plus 30 plus 12. It's 57, 58, 59, 69. Is it centimeters? Yes, centimeters. And our last example here involves particle motion. We have a particle moving along the x-axis, a horizontal motion. The velocity is given by the equation v of t equals 1 over root t for times greater than 0. At time t equals 1, its position is 4. Now this is the velocity equation. So we can let's call the position equation p of t. And then we know at time 1, so p of 1 equals 4. What is the acceleration of the particle when t is 9? Well, acceleration is the derivative of velocity. So acceleration, a prime of t, equals the derivative of the velocity. And I'm going to rewrite 1 over the square root of t as t to the power negative 1/2. So we need to take the derivative of that using the power rule. Now, once you start learning about antiderivatives, it's easy to, get confused. Am I using, the derivative rule or the antiderivative rule? But here we want to take the derivative. So our power rule is, for derivative, multiply, bring the exponent down. So multiply by the exponent, negative 1/2, t, and then subtract 1. Negative 1/2 minus 1 will look like that. And that is the acceleration equation. I don't know why I wrote a prime. I wasn't supposed to write a prime. That's just the acceleration equation, which is v prime of t. Okay, so a of t equals negative 1/2 t to the negative 3/2. And we are asked what is the acceleration at time t equals 9. So a of 9 negative 1/2 times 9 to the negative 3/2. So negative 1/2, let's deal with the negative exponent and make that 9 to the 3/2 in the denominator there. Raising to the power 3/2 means you're taking the square root and then you're cubing it. And I like to do the square root first before I cube it. So the square root of 9 is 3, and then 3 cubed is 27. So it's negative 1/2 times 1 over 27, which is negative 1 over 54. And we do not have units in this problem, so we'll just give the answer as negative 1 over 54. The next question, what is the position of the particle? So we have the velocity equation, but to find the position equation, we're going to have to take the antiderivative of velocity. So we want to integrate 1 over root t dt. And I'm going to use my trick that I showed you before because I've memorized that the derivative of root t is 1 over 2 root t. So I want to create that situation here. And I can do that by multiplying by 2 over 2. And so I very quickly know that my antiderivative is just 2 root t plus c. And now we can use this extra piece of information to solve for c. This is p of t. So p of 1, 2 root 1 plus c equals 4. So 2 plus c equals 4. C equals 2. And then I can write my position equation. P of t equals 2 root t plus 2, because that's the value of my constant. And ultimately, we want the position when t equals 9. So P of 9 equals 2 root 9 plus 2. So 2 times 3 is 6, plus 2 is 8. The position is 8. So that wraps up our lesson on antiderivatives, and next time we'll take a look at Riemann and trapezoidal sums and talk more about this integral notation. Thank you for joining.